It's literally everywhere. It covers most of our planet, it's most of what we are, and we almost never give it a second thought. But what if I told you that simple, boring water is actually one of the biggest, weirdest, and most fascinating mysteries in all of science? Yeah, let's get into it.
So why is it so weird? Well, because pretty much everything you'd expect a normal liquid to do, water just kind of does the opposite. It's like it never got the memo on the basic rules of physics. For decades, scientists have been scratching their heads trying to figure out why this simple little H2O molecule just refuses to play by the rules. And this is where it starts to get really wild. You know, you cool a liquid down, it gets denser and denser until it freezes, right? Not water. It gets densest at 4 degrees Celsius, and then it starts to expand again as it gets colder. And of course, there's the whole ice floating thing, which is incredibly rare for any substance, but also, the reason life on Earth is even possible. Then you add in the fact that it can soak up a huge amount of heat and has this super strong surface tension, and you start to see that this is no ordinary liquid.
And we're not just talking about a couple little quirks here. Scientists have found dozens of these anomalies. We don't just have one kind of ice, we have over 10 different types of ice, each with its own bizarre crystal structure. It's a whole zoo of weirdness packed into one molecule.
So how in the world do we explain all this? I mean, you'd think for the most important liquid on the planet, we'd have a nice, clean, unified theory, right? Well, about that.
The reality is, our current understanding is kind of like a patchwork quilt. We don't have one big theory. Instead, we have a bunch of separate little mini models. One model might do a decent job of explaining the density thing, another one might tackle the surface tension, but none of them talk to each other. It's like having a toolbox full of very specific wrenches, but no master key that fits everything.
This quote from the research just nails it. We have an amazing catalog of all of water's strange habits. We've listed them out, we've described them in detail, but we don't have a single story that explains the cause. We know the what, but we're still missing the fundamental why. So, what if we're looking at this all wrong? Maybe the solution isn't another little mini-model to add to the pile. Maybe what we need is a completely new way of looking at the physical world itself.
And that's where something called the Harmonic Scale Framework, or HSF, comes in. Now, this is a pretty big idea, but the gist is this. It suggests that everything in the universe, from the tiniest particle to the biggest field, is basically just a vibration, a ripple in one giant cosmic wave. It's a whole new lens to look at reality. And when you look at water through this lens, things start to click into place.
Because this framework suggests we can toss out all those complicated, separate models. It proposes that all of water's bizarre behaviors, this whole zoo of weirdness, might be controlled by one single, simple variable, a master key.
And this is it. The variable is called phi, and what it represents is something called network openness. Basically, it's a measure of how organized and spread out the connections, the hydrogen bonds, are between water molecules. You can think of it like a single master control knob for water.
And here's the real powerful part. The theory claims that just by watching how this one knob, phi, gets turned up or down by things like temperature and pressure, you can explain a whole bunch of water's mysteries all at once. Not one by one, but together as a system.
Okay, so let's put this idea to the test. Let's take that classic question we all learned in elementary school. Why does ice float?
Well, according to HSF, as water gets cold and starts to freeze, that phi value gets cranked way up. This means the network of molecules becomes much more open and structured. It's like all the molecules take a step back from each other into a more rigid formation. And that forces the total volume to expand, making the ice less dense than the water it came from. Simple, right?
All right, cool. What about that other big mystery? That weird density peak at exactly 4 degrees Celsius. How does the theory handle that one?
This is where it gets really beautiful. As you cool water down, it shrinks, just like a normal liquid would. But at the same time, as it gets cooler, that phi value is slowly starting to rise, trying to make the network expand. And at precisely 4 degrees Celsius, those two forces are in a perfect tug-of-war. The normal shrinking is perfectly balanced by the network expansion. And below 4 degrees, the expansion effect starts to win, and the water's volume increases again.
So you can see the huge difference in approach here. On one hand, you've got the old way, a whole bunch of separate models for separate problems. And on the other, you have this new idea, one single knob, phi, that connects and explains many of them together. It's a move from a bunch of short stories to one unified novel.
Now this all sounds incredibly neat, almost too good to be true. But in science, Being elegant and neat isn't enough. The single most important question you have to ask is, can we prove it's wrong?
Because that's the absolute acid test for any real scientific theory. It can't just explain stuff we already know. It has to stick its neck out. It has to make specific, bold predictions about things we can actually go into a lab and measure. It has to give us a chance to show it's false.
And the HSF theory does exactly that. It lays out some very clear, very tough challenges. First, it says that one single mathematical curve for phi has to predict the real-world data for density, heat capacity, and compressibility, all at the same time. They have to lock together perfectly. Second, it has to predict exactly how that 4-degree density peak changes when you put the water under pressure, without cheating and changing the math. And third, it has to predict a direct measurable connection between the surface tension you can see and that hidden phi value deep inside the liquid. These are real, tough, make-or-break tests.
And that really brings us to the bottom line. The theory puts all its cards on the table. This quote says it all. If that lock between all those different properties fails the test, the whole HSF idea fails. It's done. But if it holds, if the experiments confirm these predictions, then we might have just turned dozens of separate, nagging mysteries into one single beautiful mechanism and completely changed our understanding of the most familiar and yet strangest liquid in the entire universe.